Hello, everybody. Alex here, and welcome to Alex Derives Stuff. Today's derivation is going to be about that staple of calculus classes whenever you go over infinite series. There's a particular type of infinite series where you basically, ultimately, you just have to memorize whether it converges or not, and it all depends on this number p. So it's called the P-series, and there's an unfortunately named P-test associated with it. And we're going to show you, why am I saying we? I'm going to show you what values of P make it converge and what values of P make it diverge. Okay, but before we get into the specifics of this, we need some background things. We need to know about a different infinite series, the geometric series. What is the geometric series? It is, well, if x is a number between -1 and 1, then the sum as n goes from 0 to infinity of x to the n equals 1 minus x. And since for these values of x we get an actual number for the series, we say that it converges. If you prefer the longer version, of course, we could write it as, I kind of think the longer version looks a little prettier. 1 plus x squared plus x cubed plus x to the fourth plus yada, yada, yada. That adds up to 1 minus x, as long as we're plugging in a number for x between -1 and 1. Historically, the geometric series goes way back. It's probably the first ever known infinite series that anybody calculated. The earliest version of it that I know about was due to Archimedes in about 250 BC or so. He was working on the island of Syracuse, or on the island of Sicily in the city of Syracuse, and he used a geometric series to figure out what the area of a segment of a parabola was. He was basically doing calculus like almost 2,000 years before calculus was invented. So Archimedes, smart guy. The specific versions we're going to use some specific values of x. So we're going to do x equals a half. So according to that formula back there, if x is equal to a half, that series becomes 1 plus a half plus a fourth plus 1/8 plus 1 over 16. And if you plug into the formula over here, that becomes 2. So apparently this thing adds up to 2. And then at the end, when we're going to do the full generic one, we're going to say if p is greater than 1, then if x is 1 over 2 to the p minus 1. So a quick check here. So if p is a number bigger than 1, p minus 1 is bigger than 0, and then 2 to a number bigger than 0 is bigger than 1, and then 1 over a number that's bigger than 1 is smaller than 1. So this is a number smaller than 1 raised to the n, so we can plug in our x into our formula, and then this particular series adds up to whatever this is. Okay. And the idea behind our proof of convergence is we're going to somehow figure out a way to compare our p-series to one of these geometric series. And in doing so, we will show whether our series adds up to a number or it adds up to infinity. So the warm-up here. This is a special case of the P-series known as the harmonic series, and this is a very famous proof I'm about to show you. I definitely did not come up with this. This is due to a guy by the name of Nicole Oresme in 1360. So this is very old. Like there's like the plague going on around then, right? So the harmonic series is this series, the sum of the reciprocals of the integers, right? So 1 plus a half plus a third plus a fourth plus a fifth plus 6, blah, 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 blah. And apparently this diverges. This adds up to infinity, basically. And what we mean by that is if you keep adding up terms, then you're going to, at some point, you're going to get a number bigger than any preset number. So you pick a really big number, I can find a place on the series where all of the partial sums are bigger than that. And the way this works is we just sort of we split it up. So here's the first 14 terms. I picked 14 because that's how many fit on the screen. Okay, now we're going to split this up. Kind of funny. So we got 1 plus a half plus a third. So one term, 2 terms, 4 terms, 8 terms, 16 terms. And then from here on out, like the way we group all of these things is we're going to double the number of terms. So like, all right, so 1 is greater than or equal to 1. It's equal to 1, I suppose. A half is greater than or equal to 1/2. I hope everybody's cool with this so far. Now, a third plus 1/4, that's greater than a fourth plus 1/4. All right, because a third is bigger than 1/4. So if I replace the 1/3 with 1/4, okay. And so 1/5 plus 1/6 plus 1/7 plus 1/8. Well, I've got 4 terms here. 1/8 is the smallest of them. So this sum in this row right here has to be bigger than 1/8 plus 1/8, 4 1/8 added up, right? And then the same thing here. So hopefully you can see where I'm going with this. A 9th plus a 10th plus an 11th, all the way to 1/16. Every single one of these numbers is bigger than 1/16. Well, greater than or equal to 1/16. And there's 8 of them. So this is bigger than 8 1/16 added up. And then if I do the next one, then that's bigger than 16 1/32 added up. Okay, so here we can sort of see what's going on here. With my groupings, I'm finding some number that each of my groupings is bigger than. So 1 is bigger than 1, 2, 1/2 is bigger than 1/2. These next 2 terms is bigger than 2 times a fourth. These next 4 terms is bigger than 4 times 1/8. These next 8 terms are bigger than 8 times 1/16, and so on. So we can clean this up a little bit on the right-hand side. So our actual series is bigger than 1 plus a half, plus a half, plus a half, plus a half, plus a half. And you can sort of see, like, well, if I keep on going with this, then this is just going to get arbitrarily big. So this is going to add up to infinity. So therefore, the harmonic series diverges. Yeah, right on. Now, an interesting follow-up question is, say I wanted to know how many terms I would have to add up in order for this to be bigger than, say, I don't know, 1,000. And you could use this to work to get a rough estimate of that, right? You could just figure out, well, how many halves would I need to add up, and what power of 2 would I end up being at after that point. Okay, so now more generally, the P-series. So, all right, so this was the harmonic series right here. In order to get the P-series, we need to put an exponent on that n here and all of these terms. So, whoa, all right. So this is what the P-series is. Well, the sum as n goes from 1 to infinity of 1 over n to the P, where P is some specific number. So we did P equals 1. That was the harmonic series. So 1 plus 1/2 to the P plus 1/3 to the P plus 1/4 to the P. Blah, blah, blah. That's our P-series. What do we want to know about this? Well, we want to know, 1, what values of P make this converge. We already know if P equals 1, it diverges. So, okay, 1 data point. Cool. If it does converge, how close is a partial sum to the full infinite sum? Okay, so in other words, what's the rate of convergence? This I think is a more interesting question than merely does it converge. And one thing we're not going to do here is determine what the exact value of the sum is. What we're going to do is we're going to figure out a method to approximate what the value of the sum is. I don't know, there's no guarantee that it's going to be some nice number like 5 or pi or something like that. Some values of P do give you a nice number, but these proof techniques won't be able to get you that. Okay. So to start us off here, to get a feel for what the proof is, we're going to use a specific P. We're going to use probably the second most famous P series besides the harmonic series, the one where P is equal to 2. Okay, so we're making all of these exponents 2. So the sum of the reciprocals of the square numbers. And again, our first question is we want to know, well, does this add up to something? Does this end up at some finite value? And then we're going to figure out how how to put an error bound on it. So say like how good are our estimates if we add up some of the terms. So then we're going to do something similar to what we did for the harmonic series. We're going to split it up slightly differently, but so here's how we're going to split it up. We got first term, then the next 2 terms, then the next 4 terms, then the next 8 terms, then the next 16 terms, and so on. And we're going to have the direction of the inequality is going to be different here. So the 1 is going to be just that's less than or equal to 1. And the reason we're doing it this way is because we're going to show that this one converges. 1/2 or 1 over 2 squared plus 1 over 3 squared. That's less than 1 over 2 squared plus 1 over 2 squared. Why is that? Well, 1 over 3 squared, that's less than 1 over 2 squared. Okay. The next 4 terms, well, the biggest number in this list of 4 terms here is 1 over 4 squared. Each of these are smaller than 1 over 4 squared. And so that's less than 4 1 over 4 squareds added up. This next one, there are 8 terms. The biggest number out of any of these terms is 1 over 8 squared. So that's less than, sorry, the smallest number. Yeah, that's less than 1 over 8 squared plus 1 over 8 squared plus 1 over 8 squared. Okay, yeah. Yeah, and so, yeah, so 1 over 8 squared plus a bunch of stuff smaller than 1 over 8 squared. Okay. And then the next term, we have 16 numbers, each of which is smaller than 1 over 16 squared. Okay, so we could do the same thing here. Well, here we got 1 plus 2, 1 over 2 squareds, plus 4, 1 over 4 squares, plus 8, 1 over 8 squareds, and so on and so on and so on. So if we clean this up a little bit, 1 plus 2 times 1 over 2 squared, plus 4 times 1 over 4 squared, plus 8 times 1 over 8 squared, plus 16 times 1 over 16 squared, and canceling stuff gets us 1 plus a half, plus a fourth, plus an eighth, plus a 16. So our original p equals 2 series is smaller than this series, right? Like, as everything we're adding up on the left is smaller than everything we're adding up on the right. But this series on the right, this is a geometric series, right? This was the one where x was a half, right? 1 plus a half plus a fourth plus an eighth plus a 16th, which adds up to 2. So what's the result? The result is, well, our p series with p equals 2 adds up to a number that's less than 2. So it converges. By the way, it also adds up to a number that's bigger than 1. I'll leave that as a fun exercise for you to prove that the value of this sum is definitely bigger than 1. Okay. So now that we know that it converges, what then? So we know that the quote-unquote full infinite series, troubling thing about infinite series is that, you can never actually add up all of the terms in the series, but you could get a good idea of what the full infinite series adds up to by adding up merely some of the terms. Okay, so you get what are called partial sums. Those approximate the value of the full infinite series, and that's how we're going to get numerical estimates for this. And an important question then is, well, like, if I add up some number of terms and I want to get the infinite series to, say, 3 decimal place accuracy or something like that, so within 0.001, how many terms am I going to need to add? And so what we could do is we can adapt our proof just by starting at a different point in the series of convergence to find this out. So I want to start at a specific thing. So let's say I add up the first 13 terms of our series for p equals 2. So this is the sum of the first 13 squared. It goes all the way up to 1 over 169, which is 13 squared. Okay, so we're going to split this up in the same way. Now, by the way, if you're doing this by hand, we can certainly get a number for this, right? Nothing harder than long division. However, it might take like all day to do this if you're doing this by hand. So I did not do this by hand. I did this using a calculator. Apparently, this is what that adds up to. Or if you prefer to write it as a decimal, well, it's about 1.570893798. Okay, so that's what the first 13 terms adds up to. Okay. So we want to put what's called an upper bound on the rest of the series. So we want to say, well, if I add up the sums of the reciprocals of the squares 14 and above, is there some number that's less than? And we should be able to find that. And here's how we do it. So we go so first we do all of the terms from 14 to 26, so 2 times 13. And then we do all of the next term, 2 times 13 plus 1, so 27, I guess, all the way to 4 times 13. And so notice in this first grouping, there's 13 terms. In this second grouping, there's 2 times 13 terms. And then in this third grouping, from 4 times 13 plus 1, all the way to 8 times 13, there's 4 times 13 terms, and so on and so on and so on, right? So we're splitting it up in the same way, except like we're starting with a grouping of 13. So this first grouping, well, every single one of these numbers is less than 1 over 13 squared, right? And there's 13 terms, so this is less than 13 times 1 over 13 squared. This second grouping, every single one of these numbers is less than 1 over 2 times 13 squared, and there's 2 times 13 of them, so there's 2 times 13 times 1 over 2 times 13 squared. This third grouping, every single term is less than, every single number in this bit is less than 1 over 4 times 13 squared, and there's 4 times 13 of them. And same thing here, next grouping, every single number is less than 1 over 8 times 13 squared, and there's 8 times 13 of them, and we can keep going. And in much the same way, this thing simplifies, right? We can cancel stuff. So let's cancel, and we're left with 1 over 13 plus 1 over 2 times 13 plus 1 over 4 times 13 plus 1 over 8 times 13. So the whole series on the left, 1 over 14 squared plus the rest of the series, is, all right, I can factor out a 1 over 13, so it's 1 over 13 times 1 plus a half plus a fourth plus an eighth. So there's our geometric series again. So the rest of this series is definitely less than 2 over 13. So what do we got so far? Well, we figured out through, well, having a computer doing all of the addition for us, that the sum as n goes from 1 to 13 of 1 over n squared is about this number. Okay. And the rest of the series, whatever it adds up to something less than 2 over 13. So what can we say about the full infinite series? Well, the full infinite series would be between whatever the first 13 terms adds up to and the first 13 terms plus this sort of upper bound on our error. Okay, so we can convert this right thing to a decimal, and we get, all right, so the sum as n goes from 1 to infinity of 1 over n squared is between 1.57089 and 1.72473. So it's a loose upper bound. So it's about like 0.15 difference roughly between these two numbers here. So it's not the best estimate in the world if I just do 13 terms, depending on how precise I want to be. Okay, so if we want to make this more general, well, okay, so I just picked 13 at random here. So what if I just picked any number of terms? What's the upper bound on the error? So if I add up the first big N terms, okay, so that adds up to whatever that adds up to. It's some grunt work for any specific value of n, right? Or better yet, have a computer do it for you. And we want to find an upper bound for the remainder. So we want to know a number that's bigger than whatever, that's definitely bigger than whatever the rest of the series adds up to. Okay, so we split it up in the same way. So here, so the rest of the series, 1 over n plus 1 squared plus 1 over the next number, n plus 2 squared, plus da 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 da. So we have n terms here, right? Because we're going from n plus 1 to whatever 2 times n is. So recall, like before we did this, this was when it was n was 13. This was like this was 14 to 26, right? So there's n of these terms, and each of them is smaller than 1 over n squared. So you get, that's less than n over n squared. Okay. The second line here, we have 2n terms, and each of them is smaller than 1 over 2n squared. Okay, so there's 2n. Cool. And then for this next line, there's 4n terms, and each of them is smaller than 1 over 4n squared. And for this last line, well, it's not really the last line. It's the last line I had room for, but you can continue the pattern. There's 8n terms, and each of them is smaller than 1 over 8n squared. And then we can clean this up a little bit, right? We can cancel stuff. And so we get from n plus 1 to infinity, our series is less than 1 over n plus 1 over 2n plus 1 over 4n plus 1 over 8n. And if we factor out the 1 over n, we get our same geometric series with a 1 over n factored out. And so we get the error in our partial sum is less than 2 over however many terms we decide to add up. So if we compute the sum to big N terms, we will be off by less than 2 over big N. All right, so yeah, the sum as n goes from big N plus 1 to infinity is less than 2 over big N. Cool. Now, so this is an upper bound on our error. So if we want to know, well, like say, so if we want to add up enough terms to get the infinite series to within, say, 0.001, I picked that number kind of arbitrarily. We got, well, how many terms would we need to add up? We just need to find a big N so that 2 over big N is less than 0.001. Okay, let you think about that for a second. Hint, 0.001 is 1 over 1,000. So N would have to be bigger than 2,000? Yeah. All right, so in order to get, say, about 3 decimal place accuracy, I need to add up 2,000 terms of this series. All right, now if adding up the first 13 terms of this series would have taken you all day if you did it by hand, certainly adding up the first 2,000 terms of this series would take you like a week. So, but let's calculate it because, you know, we live in the future, so we have computers and stuff. So we could say that the full infinite series is about approximately squiggly equal to just the sum of the first 2,000 terms. And if we have a computer do this for this, I just plugged it into Wolfram Alpha, we get about this number, 1.6444342. Okay. And then we know that the error, because we did the, you know, we had a way of calculating the error separately, right? The error is less than 0.001. And so that means that the actual value of the sum is somewhere in between this approximation and the approximation plus the error. So this would be, this is just what you get, right? I just added a 1 in this slot right here, right? So this is between 1.6444342 and 1.6454342. Well, that's a bit of a tighter bound. For a lot of practical purposes, this might be a good enough estimate for the full infinite series. I suppose if you want a better estimate, you could average these two numbers. Actually, I worked it out. If you average these two numbers, you get a really good estimate. You get like 6 decimal place accuracy or whatever. So it's pretty wild. Okay, so that's p equals 2. So we now know for sure that, well, the first thing we did was that this diverges if p equals 1. That was the harmonic series, right? So effectively, if p equals 1, this series adds up to infinity. And we know it converges if p equals 2. The very first thing we did with that one was we showed that the whole series is less than 2. And in fact, we got tighter bounds on this. So knowing just these two facts, we can, well, there's some easy things we could do for other values of p. So one, we could show that it diverges if p is less than 1, basically by comparing it to the harmonic series. So I'll leave the details of that to you. We can also show that it converges if p is strictly greater than 2, because we know it converges if p equals 2, and we can compare it to this dude. Okay. So what does that leave us? It leaves us values of p strictly between 1 and 2, right? Like, what about p equals 1.5 or 1.2 or 1.17436? Well, what we could do here, we could rework the same proof that we did for p equals 2, except just leave the p's as p's and just assume that p is just some number bigger than 1. Okay. So we split it up in the same way as we did with p equals 2. So we got 1 plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p plus 1 over 5 to the p, plus 1 over 8 to the p all the way to 1 over 15 to the p plus 1 over 16 to the p all the way to 1 over 31 to the p, and so on and so on. And so again, the way this grouping works is we got 1 term, 2 terms, 4 terms, 8 terms, 16 terms, the next one will be 32, and so on. And each chunk, we're doubling the number of terms, and we could just go through chunk by chunk and find something that this is less than. So 1 is, of course, less than or equal to 1. The second chunk is less than or equal to 1 over 2 to the p plus 1 over 2 to the p, right? Because if p is bigger than 1, well, if p is positive, actually, then 1 over 3 to the p is less than 1 over 2 to the p. Then this next chunk, there's 4 terms, each of which is smaller than 1 over 4 to the p. Next chunk, there's 8 terms, each of which is less than 1 over 8 to the p. Next chunk, there's 16 terms, each of which is less than 1 over 16 to the p. Okay, so then, of course, we can split it up. So, right, there were 2 chunks of 1 over 2 to the p here. There were 4 chunks of 1 over 4 to the p here. There were 8 chunks of 1 over 8 to the p here. There were 16 chunks of 1 over 16 to the p here, and so on and so on. And we can clean this up a little bit, right? So we can subtract 1 from the exponent on the denominator. So now, here we've got to be a little bit tricky here. So 4 is the same thing as 2 squared. And so if we have 2 squared to the p minus 1, you can write as 2 to the p minus 1 squared. And so we can actually split this up like this. So 1 over 2 to the p minus 1 squared. These are equivalent. You can check. You get the same exponents here. All right, and then this is our geometric series where the x was 1 over 2 to the p minus 1. And the big thing to remember is that we assume if p is greater than 1, then this x here, this stuff in the parentheses, that's going to be less than 1. And so that means that this series converges, and we can actually figure out what the value of the sum is, right? Because we just plug in our x. So 1 over 1 minus 1 over 2 to the p minus 1. Feel free to simplify that if you like. So as long as p is strictly greater than 1, then our p-series converges. So we have this very weird thing going on here where, like, if p is equal to 1, we get a divergent series, but if p was equal to 1.000000000000001, that would converge. That would add up to some number. It might converge very slowly. It might take a lot of terms to get any kind of accuracy, but yeah. So there's our results. Okay, so what did we do here? What are some big picture things? So to prove all of this, one, we needed to know about the geometric series. So a lot of what you do with infinite series is you start with the geometric series and then maybe a telescoping series and see how that works. And then you use those to figure out results about other infinite series, and then you slowly build up your library of infinite series that you know about. So this p-series here would be the next sort of infinite series in your library, and you can say, like, okay, so now I can use these p-series as a basis to figure out whether some other infinite series converge. Okay, so yes. So first you need to know about the geometric series, then you can use the geometric series to prove stuff about the p-series. And so our main technique, we basically had to somehow figure out a way to group our terms together or break up our series into chunks. And we had to do that in such a way that we could compare it to a geometric series. Okay, and so in this case, it was breaking it up by 1s, 2s, 4s, 8s, so like doubling the number of terms each time. And so a little mini alteration of this technique allowed us to put an upper bound on our error. So it would say, like, well, what if I wanted to sum the terms from like 1,000 to infinity? I was like, could I put an upper bound on that? All right, so to see if you understood this, here are some exercises for you that will use some similar techniques. So here's one of them. Here's another famous series. The sum as n goes from 0 to infinity of 1 over n factorial. So remember, 0 factorial is 1. So this would be the series 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on. So you can adapt the proof method that we used here to show, 1, that this series converges, and 2, show that the partial sum approximates the infinite sum where this would be the error term. Okay. So in other words, if I added up the terms from big N plus 1 to infinity, that's always going to be less than this number right here. Okay, so that's one thing that you can prove. And this one, hopefully, if you write it out sort of the long way, it will be relatively easy to prove. The standard way of showing that this converges uses the ratio test, which honestly is the same thing as comparing to a geometric series. So now the proof technique we did was a illustration of something called the Cauchy condensation test. So you can use this technique to derive the Cauchy condensation test, which is this is not one of the standard convergence tests for some reason. This is usually reserved for an upper division course, but but using this same technique, you can derive it. So basically, if you have a positive decreasing sequence of real numbers, so A1, A2, A3, so basically all the numbers in this list are positive. It's an infinitely long list, and each number is less than the previous number. And I believe this works if it's less than or equal to. Then what you could do is prove this: the sum of an converges if and only if the sum of 2 to the n, a2 to the n converges. And the way you can prove this is doing the same stuff that I did to show that the P-series converges. All right, so now you know a little bit more about the P-series than you did before, hopefully. And I will be back soon with yet another derivation.